Hello, this is Jack Jackson. In this video, we're going to be talking about the technique of partial fraction decomposition. In the last video, we quickly reviewed how we could add fractions, and let's go over that again. So we have 3 over x plus 2 plus 4 over x plus 5. We factor the denominators. These are prime denominators, so we leave them like they are. And we get a common denominator. In this case, we multiply the top and bottom of the first fraction by x plus 5, and x plus 2 is what we multiply the bottom and the top of the second fraction by. So that first fraction is equal to this, second is equal to that, so that equals is valid. Distribute in the top, we get 3x plus 15 and 4x plus 8. Okay, continuing on, now that we have two fractions with the same denominator, we keep that denominator and add the numerators. 3x plus 15 plus the 4x plus 8. Combine like terms, that's 7x plus 23. Factor the top and cancel if we can. It looks like our final answer is 7x plus 23. If we wanted to, we could FOIL out the bottom, distribute property, multiply it out to get x squared plus 7x plus 10. Now, and this version right here is actually probably the best version to leave it in. But the point is we can take something that looks like this, 3 over x plus 2 plus 4 over x plus 5, and with this technique we can change it to something that looks like 7x plus 23 over x squared plus 7x plus 10. So we should be able to do this backwards. Start with this final answer and end up with what we have at the beginning. That technique is called partial fraction decomposition. Now let me warn you, before we start, we only apply this process to proper fractions. So this only really works with proper fractions. So the numerator has to be strictly smaller degree than the denominator. Okay? So when we have rational expressions like this, we can do this. So the trick here is, here's the technique. We first factor the denominator and get it in this form. So if we start with this bottom form, we go back one step to there, which is just factoring. Now, what we want to do is we want to get it into the form of a over the x plus 2 plus b over the x plus 5. Now, since we've already done this, we know a is 3 and b is 4, but at this point in the reverse process, we don't know that yet. So, what do we do with this? Let's see. What we're going to do is take both sides of the equation and multiply by this common denominator of x plus 2 times x plus 5. On the left, it will cancel out completely, leaving 7x plus 23. On the right, it will distribute, and the first part, the x plus 2's cancel, leaving the x plus 5 times a, and the second part, the x plus 5's cancel, leaving the b times the x plus 2. Now, there's a couple of different ways of going at working this out, but this is the way I'm going to show you. It's called the Annihilator Method, or the Annihilation Method, and I think it works the best. At least I like it better. What we're going to do is these are equal as polynomials. That means no matter what we plug in for x, as long as both sides of this equation are defined, they're going to be actually equal. And of course, a and b are constants. So what we do here is plug in some good choices for x. And the x's are going to be things that are going to annihilate these fractions, these factors here. So for example, if I pick x equals negative 5, this will be negative 5 plus 5 is 0 times a is 0, so this part goes away. And that's what I'm going to do first. If x is negative 5, I plug it in here, 7 times negative 5 plus 23, and plug it in here. This term right here with the a goes away, so a is out of the picture. Negative 5 plus 2 is negative 3, so we get negative 3b is, let's see, 7 times negative 5 is negative 35 plus 23 is negative 12. Divide both sides by negative 3, and we get b is 4. Similarly, if we use x is negative 2, it will annihilate this term, annihilate the b's. So we plug in x is negative 2 here. And by the way, if it didn't annihilate, we could go ahead and plug in b is 4. We know it's 4 at this point. But either way, it doesn't matter. This term is 0, so it goes away. Let's see, negative 2 here gives us a 3 times the a. And negative 2 here gives us negative 14 plus 23, that's 9. And then divide by 3, we get 3. And so we see that the 3 goes for the A, 4 goes to the B, and that is exactly what we started with way back up here. So that process allowed us to reverse partial fractions. Now, why do we need to do that? Well, we're going to want to do that for finding antiderivatives, because the thing on the left is nasty to find an antiderivative of, but the thing on the right is actually easy to find an antiderivative of. So we want to find the family of antiderivatives of 7x plus 23 over x squared plus 7x plus 10. Then we break that into the integral of the right side, which can be broken into 2 integrals, and the constants brought out front. So it's 3 times the integral of 1 over x plus 2 dx, and plus 4, the integral of 1 over x plus 5 dx. And this antiderivative is easy. We just let u be x plus 2, du is dx, and the antiderivative is log of the absolute value of x plus 2. We still got our 3 out front. Similarly, say w is x plus 5, dw is dx, and this becomes 4 natural log of absolute value of x plus 5. Of course, always have your plus c at the end. Now, the fundamental theorem of algebra, one version of it, tells us that any polynomial function with real number coefficients can be factored down into a product of linear and quadratic factors that are irreducible over the real numbers. If we can find these factors, that's sometimes easier said than done, but if we can find them, when we list the terms for the partial fraction decomposition, every one of those linear factors in the denominator gets an unknown constant numerator, and every quadratic factor in the denominator gets a linear numerator with unknown coefficients. If the factor is repeated n times in the numerator, then we have to list n terms for it with powers 1, 2, 3, up to n on the factor in the denominators. If the factor is a linear factor, then the numerator is still just a known constant regardless of the power, and similarly for quadratic factors. And here are some of the examples of that step in the partial fraction decomposition. Capital letters and the unknown constants that we have to solve for. It's really easiest to see this with a few examples, so let's look at it. So here, the denominator can't be factored anymore. It's got a prime or irreducible linear factor, x plus 1, and a prime quadratic factor, x squared plus 4. The x plus 1 has a constant on top. It has to be a proper fraction, so it's going to have just a constant on top, so it's a over x plus 1. And the quadratic factor on the bottom is x squared plus 4. The numerator has to be a smaller degree, so it could be a linear factor. It could be bx plus c. So we got 3 unknowns to solve for there. Okay. If you have x plus 5 squared, you put an x plus 5 and then an x plus 5 squared. You need both of those to show up. But since it's linear here, we just need an a and a b. Even though this is, if you squared it out, it's a quadratic, this doesn't get a bx plus c. It only needs a b there to work out. This one's got a lot of unknowns in this one, but if you have 2x plus 3 over x plus 1 cubed times x squared plus 4 squared, well, the x plus 1 cubed is going to show up as an x plus 1, x plus 1 squared, and x plus 1 cubed. And the coefficients in the top are just a, b, and c, constants, because we have linear factors. This quadratic thing, since it's the second power, is going to show up to the first and the second power in its own denominators, each in its own denominators of its own fraction. And the numerator is going to be linear, 5 dx plus e, and then fx plus g. Let's finish this for the other one. So let's just take this first one up here and take it and see if we can finish out the rest of the process. Okay, so you might try it yourself. See if you can do it yourself. Press pause now. Okay, you're back now. Let's try to do this. We multiply both sides of the equation by the common denominator of x plus 1 times x squared plus 4, leaving only the numerator on the left. In the right, we distribute. In the first part, the x plus 1's cancel, leaving an x squared plus 4 times the a. Plus, of course, the second one, we have the bx plus c times x plus 1 because the x squared plus 4 canceled. Now, it's pretty easy to eliminate both b and c at one fell swoop by letting x be -1. So let's do that first. And if we let x be -1, this whole last part here becomes 0. -1 squared is 1 plus 4 is 5, so this gives us 5a. 5 times -1 plus 2 is -5 plus 2 is -3. Divide by 5, a is -3/5. Now at this point we can put in a is -3/5 in any point from this point on. Now it's not so easy to just eliminate the a here, although now we know what a is, because there aren't any real numbers that we can put in here to make this 0. We could use some imaginary numbers, I and 2i, but that gets a little messy. So it's best if we just stick with real numbers. We can actually eliminate the b by letting x be 0. So I'm going to do that next. But this time, remember, we know what a is, so we can plug that in. And I plug in 0. That's going to eliminate the b. 0 plus 1 is 1 times c is c, so that just gives us c there. 0 squared plus 4 is 4 times -3/5 is -12/5. 5 times 0 plus 2 is 2. So not only does that eliminate the b, 0 is an easy one to work out a lot of times because a lot of the parts of it go away, specifically the b and then also this 5 and so forth. So it's worked out pretty nicely. So then we just add 12/5 to both sides. 2 is, see, multiply top and bottom by 5, it's 10/5. Plus 12/5 is 22/5. Well, now we know b and c, we can substitute those in, and I just need to plug in something else, really anything else. There's nothing nice that sort of eliminates anything at this point, but what we can do is just plug in any other number and solve the resulting thing. So probably about the easiest thing I could think of was 1. So I plug that in. And 5 times 1 is 5 plus 2 is 7 there. 1 squared is 1 plus 4 is 5 times -3/5 is -3. And then we got b times 1. Let's see how we got to do this out here too. 1 plus 1 is 2. Distribute times the b is 2b. The 2 times the 22/5 is 44/5. Notice I have substituted in the known value of a, -3/5, and c, 22/5. And now I'm going to just solve for b. Not too bad here. Let's see. Let me first add 3 to both sides. That makes that a 10. Then subtract 44/5. Get a common denominator. 50/5 minus 44/5 is I think that's positive. Let's see. It's positive 6/5. Let me fix that. Because we're adding, yeah, that's correct. Okay, made the corrections there. So that's positive 6/5. And then divide by 2, that cancels the 6 down to a 3, so that's positive 3/5. Okay, and then let me change this. And math type here, let's see what we've got. That's the one, let's see. So b was positive 3/5, so let me get rid of that and make this a plus. So I can think of this as -3/5 times 1 over x plus 1. 3/5 times x over x squared plus 4. And plus 22/5 times 1 over x squared plus 4. I did that like this because in the next step of doing this in an antiderivative, this is going to be the best thing, best way to have it. I believe this was a plus 3/5. We fixed that. But then notice it's pretty easy to find antiderivatives in that last form. Let's look at it here. 5x plus 2 over x plus 1 times x squared plus 4. Again, that's -3/5 times this integral, this one, and this one. We've got those integrals. We've got the coefficients out front. So when we find an antiderivative 1 over x plus 1 dx, just let u be x plus 1, du is dx. So this is the logarithm of the natural logarithm of the absolute value of x plus 1. We've still got our negative 3/5 out front. This is going to have a 3/5 out front. This one here, we let u be the denominator, x squared plus 4. Du is 2x dx. So if I just put a 2 with the dx that I have, then I need to put a 1/2 out front, making this 3/10. What I get is 1 over u du. So that's the natural logarithm of the absolute value of x squared plus 4. But x squared plus 4 is always positive. In fact, it's always at least 4 or higher. So we don't have to need we can just drop the absolute value there. Now the last one, 1 over x squared plus 4 dx, that's 1 over x squared plus 2 squared, so that's just an arctangent for the antiderivative, the arctangent of x over a. So 1 over x squared plus a squared is actually 1 over a times the arctangent of x over a. So that's x over a here. The 1 over a is 1/2, is why that 22 went down to an 11. And when our last integral sign disappears, of course, we always put the plus c. So this last step here is relatively straightforward. A couple of easy substitutions, a basic arctangent, and some logarithm antiderivatives there, and we're pretty good to go. So the key part is to break it down those partial fractions. One more time, let me remind you that this partial fraction decomposition technique is only applied to proper fractions. If the fraction is improper, then use long division to write it as a polynomial plus a proper fraction, and then apply the partial fraction decomposition to the proper fraction portion.